Now let's talk about Hund's rule. Uh, this is also called as Hund's rule of maximum multiplicity. And what's the question in our mind before going into the Hund's rule is that for example, if we take a p orbital, and this p orbital, because we have Pauli's exclusion principle, and this p orbital has three states, but all of these three states have same energy. Now let us assume this is px, this is py, and this is pz. Now, for this p orbital, px, py, pz, the energies are same, and we call these states as degenerate states. Whether you call them states or levels, the choice is yours. Now the question is that how should electrons be filled in these orbitals? That's an important question. I mean, if I take an example in which we have three electrons to be filled in the p orbital, there can be two possible ways. One, we can have 1 and 2 and 1. And there is another possibility, that is px, py, and pz can have 1, can have 1, can have 1. Now, which of the two states is correct? That's a point of contention here. And the answer to this problem was given by Hund, and that's why we have a rule here known as Hund's rule. And what this rule states is, it tells us that when we have more than one orbital, as is the case here, of equal energies available, then the electrons will first occupy these orbitals separately. So if I have four electrons, first three electrons will occupy the three orbitals separately first, with parallel spins. So 1, 2, and 3, if I assume that I have four electrons. And the pairing of the electrons will start only after all the orbitals of the given level are singly occupied. Now the fourth electron will start pairing. It will start pairing the first one. So this is what Hund's rule states. Now, according to the Hund's rule, the correct way of filling three electrons in the p orbital that we have here is that in which orbital we have electrons singly occupying these orbitals, and their spins are parallel. And if we have this kind of situation, this is violating the statement of Hund's law. And this Hund's rule is what's termed as the Hund's rule of maximum multiplicity. So in the same case, if we take with d orbital, degenerate orbitals of d, which has 5 orbitals in it. So suppose I have to have say I have 6 electrons to be distributed among these orbitals. Then the first important thing is that first electrons are going to occupy all the orbitals with their spins parallel. And when these orbitals are filled, the additional electrons will be used for the pairing purpose of these orbitals. Now, in order to understand this thing, two electrons with parallel spins, if we have two electrons with same spin, they tend to be as far apart as possible in order to minimize the electrostatic repulsion. right? So therefore, the electron prefers to occupy the orbitals which singly. They prefer to occupy orbitals singly as far as possible, and either to pair up with now if I say that when all the orbitals get singly occupied, as in this case all the electrons are singly occupied, then the incoming electron has two choices: either to pair up with the other electron or to go to the next higher orbital. So the fourth electron that I will have here, it has only two choices. Either it will prefer to pair, or it will prefer to go into the next higher orbital. When a vacant orbital of a suitable energy is not available, then this incoming electron will have no choice except to pair up with another electron. So the point is, the choice, it has to choose the lowest possible energy state. So if it does not have the choice available of the suitable energy, what it does, it goes and pairs up with with the electron in the given orbital. And if we take an example, say for example, to be more concise, if we take an example of, say, nitrogen, okay, nitrogen has it has 7 electrons, and we can fill the electrons in nitrogen atom using Aufbau principle, that is 1s, 2s, and 2p. So since each orbital can accommodate only 2 electrons, at the maximum, in view of Pauli's exclusion principle. Hence, the electronic configuration of this nitrogen will be 1s2, 2s2, and 2p3. That's going to be the case. And since there are 3 p orbitals, and these p orbitals are degenerate, that means their energies are same. Hence, the possible distribution of electrons under consideration of Hund's rule will be what? So on applying Hund's rule here, what we will have is 1s2, then 2s2, and then we will have 2px1, then we will have again 2p y1, then again we will have 2pz1. Okay, so that will be the case. And if we have to show it in terms of boxes, there's no need to show it like that. We can have pairing, then we have pairing, then we have 1, 2, and 3. So this is my 1s, this is my 2s, this is my 2px, this is 2py, and this is 2pz. So this is how electrons prefer to be in the orbitals in accordance with Hund's rule.